Hello students, welcome to Jce Connect. We are discussing module 4 of the subject Basic Electronics, and so far in the previous 4 lectures we have studied 2 important concepts in this module, that is about BZA application and feedback amplifiers. Now we are entering into the last part of this module, that is oscillators. So in this last section of this module we are going to discuss about what is oscillator, how oscillators can be classified, what is Markuson criteria of oscillation, what is the effect of loop gain on the oscillations generated, and then we are going to discuss about 2 important RC oscillators called RC phase shift oscillator and Windbridge oscillator. And at the end of this module we will be discussing about what is IC 555 timer and how this 555 timer can be used as an astable multivibrator. So these are the things we'll be studying in this last part of this module called oscillators, maybe in this lecture, and some of the concepts we'll be discussing in the next lecture. So we'll start today's lecture with defining oscillator. So what is an oscillator? So we can have various definitions for the oscillator. So as the name itself indicates, oscillator, the one which oscillates or one which generates oscillations or repeated waveform without any external input, is called as an oscillator. That is, oscillator is a circuit which will produce a repetitive kind of waveforms without any external inputs, or we can define it as a circuit that produces periodic waveforms at its output with only the DC biasing supply given to it and without any external AC input. That means oscillator will not have any external AC input. Whatever the DC biasing supply we are giving to the oscillator, that itself will be converted into AC oscillations. Hence we can say that oscillator converts DC into AC, and hence we can call the oscillators as signal generators. So oscillator can generate various kinds of periodic or repeated waveforms without any external input. So this particular figure clearly illustrates what exactly an oscillator is. Here I have shown a block diagram of an oscillator, and you can see here there is no external input. Then you may ask, something is shown here, that is what is called as the DC power supply, right? This is not an external input applied to it. It is a DC power supply which is required for the biasing of the amplifier which is used in the oscillator, and this DC itself will be converted into AC oscillations. And as I told, oscillators generates periodic or repeated waveform, and the frequency of the generated waveform depends upon the various components that are used in the oscillator circuit. So here we have shown this oscillator. It can generate a periodic waveform like this, which is called as sine wave, or it may generate like this, which is called as square wave, or it may generate a sawtooth signal or a triangular signal. So any kind of a repeated or periodic waveform can be generated using an oscillator without any external input, just by giving the DC power supply, and that electronic circuit is called as an oscillator, right? So once again I am repeating, oscillator will not have any AC input, unlike your amplifiers. Here whatever the DC supply is given for as a biasing voltage to the amplifier present in the oscillator, that itself will be converted into AC oscillations of a particular amplitude and particular frequency. That is what is called as oscillator, and it can generate sinusoidal signal or a non-sinusoidal signal like square wave, sawtooth wave, triangular wave, etc. And the frequency of the generated wave depends upon the constituent components that are used in the oscillator. Now, what is the major difference between amplifier and oscillator, which is very much clear here in this particular slide. You can see the first diagram is of amplifier. So amplifier always need a biasing supply voltages. Some amplifiers need like single power supply, some needs dual power supply, like one we have studied, operational amplifier. Operational amplifier needs dual power supply like plus VCC and minus VCC. Right? Some other amplifiers which are constructed using transistors, they may need only single power supply like VCC, which we connect normally in the collector of the transistor. So biasing DC voltages are must for the amplifier, either single supply or dual power supply, right? So this is called as the biasing supply. Now what is the functionality of the amplifier? Amplifier increases the strength of the input weak signal. That means definitely you have to connect a small input, and that small input will be converted into larger output, and that circuit we call it as an amplifier. So compulsory in amplifier input is must, and this input is converted into bigger output in case of amplifier. But now if you see the block diagram of an oscillator, what is shown here? Again the biasing is must, because here also we may use either a transistor or the operational amplifier. If you use a transistor, single power supply is sufficient, and if you use the operational amplifier, then you may have to go for dual power supply. So biasing supply is must in case of oscillator also. But the major difference between this and this you can see here. Here in the oscillator there is no input, whereas there is an input in the amplifier. So without any input, just by using this DC power supply, you will get the output in the oscillator. That's why oscillator on its own, it generates the output signal which is repetitive or periodic in nature. I hope it is clear. Once again I am repeating here, in amplifier we are giving a small input and we are getting a larger output, whereas in oscillator we are not giving any external AC input, only the DC power supply is given, and the DC power supply itself will be converted into AC oscillations, either sinusoidal or non-sinusoidal, and that circuit we call it as oscillator. Now next we will see how we can classify oscillators. Right? Again here it is we can classify the oscillators into different categories based on different criterias. Like the first one which I have shown here is the classification of oscillator based on the output waveforms. That means what kind of output waveform the oscillator is producing or generating. We can classify oscillators into two different types, and those are called as sinusoidal oscillators or harmonic oscillators, and relaxation oscillators or non-sinusoidal oscillators. Now what do you mean by sinusoidal oscillators or harmonic oscillators? Right? Sinusoidal oscillators are nothing but the oscillators which generates sinusoidal signals or a sine wave. The simple example you might have studied already in your pre-university course also, a simple pendulum. If you take the example of a simple pendulum, to and fro motion of that simple pendulum is nothing but harmonic in nature or the sinusoidal. So such oscillations we can call it as sinusoidal oscillations. And the oscillator which generates such sinusoidal oscillations or harmonic oscillations are called as sinusoidal oscillators. Whereas relaxation oscillators, if you see the previous slide, here I have shown different kinds of waveform. This is called as sinusoidal, and these two waveforms are called as non-sinusoidal. That means any waveform which is not sinusoidal is called as non-sinusoidal, and the oscillator which generates such non-sinusoidal oscillations or which generates non-sinusoidal signals are called as relaxation oscillators. Right? Or sometimes they are also called as non-sinusoidal oscillators itself. Example for non-sinusoidal oscillators are the square wave generator, sawtooth generator, like triangular wave generator, etc. All comes under what? The relaxation oscillators. That is, as I said in the introductory remark, that is we are going to discuss about 555 timer as a astable multivibrator, and that astable multivibrator also comes in the category of relaxation oscillators. Then the next important classification of the oscillator is based on the feedback circuit employed. Right? So here you have to remember, whenever you are discussing about the oscillator basically makes use of amplifier. Along with the amplifier, oscillator makes use of positive feedback. This is very important thing about the oscillators you have to remember, which I already explained you in the previous lecture. That is, almost all amplifiers makes use of negative feedback, whereas oscillators makes use of positive feedback or regenerative feedback. And already I told you what is positive feedback. A positive feedback is one in which the feedback signal will be in phase with the external input signal, and as a result effective input applied will be more, and hence the gain will be more. Positive feedback increases the gain, and such positive feedback is used in oscillators. So based on what kind of feedback circuit you are using, that means what are the constituent element of the feedback circuit, we can have two different types of oscillators, and those two different types of oscillators are called as LC oscillators or RC oscillators. Now what do you mean by LC oscillator? Here L stands for inductance and C stands for capacitor. So obviously the oscillator which makes use of inductance and capacitance as a feedback circuit, then that type of oscillator is called as LC oscillator. Normally in LC oscillator, inductance and capacitance are connected in parallel like this. We will be having an inductance and then we will be having a capacitance. Here like output will be given and this is given to the feedback. Such type of circuit is called as tank circuit. Parallel combination of L and C is called as a tank circuit, and the oscillator which uses tank circuit as a feedback element is called as LC oscillators. Normally these LC oscillators are used to generate high frequency oscillations or high frequency signals, and the examples of the LC oscillators are Hartley oscillator, Colpitt's oscillator, or even we can consider crystal oscillator as a part of LC oscillator. That is Hartley, Colpitt's, crystal oscillator, they can come under the category of LC oscillators because they make use of inductance and capacitance connected in parallel called tank circuit as a feedback element or feedback circuit. Right? Then the next type of oscillator according to the feedback circuit employed is called as the RC oscillators. Again, as the name indicates, here L is replaced by R, means the oscillator which makes use of resistance and capacitance as what? Feedback element or a feedback circuit is called as RC oscillator. And normally these RC oscillators are used to generate low frequency oscillations, right? Because LC oscillators can generate a very high frequency signal, and those LC oscillator we cannot use at low frequency because at low frequency the values of inductance and capacitance becomes bulky. So normally, and the stability also is an issue, hence LC oscillators are not used for low frequency oscillations. So when you want to generate a low frequency oscillations, obvious choice is the RC oscillators, which makes use of resistance and capacitance as the feedback circuit, right? So there are various RC oscillators like RC phase shift oscillator, Wien bridge oscillator. All these are the examples of the RC oscillator where they use resistance and capacitance as the feedback element. In fact, in this module we are going to discuss two important RC oscillators, that is called as RC phase shift oscillator and the Wien bridge oscillator. LC oscillators are beyond the scope of this particular syllabus. As I said, there are various types of LC oscillators like Hartley oscillator, Colpitt's oscillator, crystal oscillator. Those are used for high frequency oscillations. So anybody interested in that, you can have, there are a lot of resources available. You can just have a look at those oscillators too, right? That is the second type of classification of oscillators. Then third type of classification is based on the operating principle, how the oscillators are classified. That is, based on the operating principle, The oscillators can be classified into two types. One is called as negative resistance effect oscillators, right? There are certain devices which exhibits negative resistance property, and by utilizing this negative resistance property of the devices, we can generate the oscillations, and those oscillators are called as negative resistance effect oscillators. Whereas normally we go for what are called as feedback oscillators, right? So the oscillators which makes use of positive feedback to generate the oscillations are called as feedback oscillator. That is the third type of classification of oscillators. And there is one more important type of category of oscillators, that is based on the frequency generation. Based on what is the frequency generated by the oscillator, we can classify the oscillators into different types or different categories. The first one is called as audio frequency oscillator. Like as the name itself indicates, you know that. What do you mean by audio frequency oscillator? The oscillator which generates frequency in the range of audio frequency band. That is, the oscillator which generates a frequency in the band of 20 Hz to 20 kHz is called as audio frequency oscillator, because already you know the audio frequency range or the audio frequency band is of 20 Hz to 20 kHz. So the oscillator which generates frequency in this range is called as audio frequency oscillator. Similarly, the second type is radio frequency oscillator. The radio frequency range, you know, 20 kHz to 30 MHz. The oscillator which generates a frequency in the range of 20 kHz to 30 MHz is called as radio frequency oscillator. Similarly, the oscillator which generates a frequency in the range of 30 MHz to 300 MHz is called as very high frequency oscillator. The next level, that is 300 MHz to 3 GHz, is called as ultra high frequency oscillator. Then the microwave oscillator generates a frequency in the range of 3 GHz to 30 GHz, and anything above 30 GHz is called as millimeter wave oscillator. Right? So this is how, based on the frequency generated by the oscillator, we can classify the oscillator into the 6 different types. That is audio frequency oscillator, radio frequency oscillator, very high frequency oscillator, ultra high frequency oscillator, microwave oscillator, and millimeter wave oscillator. So this is how we can classify the oscillators into 4 different categories. Right? Now, after knowing what is an oscillator, what is the property of the oscillator, how oscillator is different than the amplifier, and the different types of oscillators, now we are going to study a very important concept in oscillator called Markuson criteria of oscillation. Now, what exactly you mean by this Markuson criteria of oscillation? And this criteria can be stated by considering the block diagram as shown in this particular slide. If you see this particular block diagram, it is almost similar to the block diagram which we have discussed in the feedback amplifiers, but it is not exactly same. There is one very important difference between the block diagram of the negative feedback amplifier and this amplifier. Can anybody tell me what is that? Yes, you can see here the feedback signal is what? It is in phase with the input signal. Therefore, here there exists what is called as positive feedback. So we can call this particular circuit or block diagram as a positive feedback amplifier, right? Because almost everything is same here. Only thing, feedback signal and the input signal, they are in phase. So this particular block diagram represents a positive feedback amplifier. Now if you see here, what are the different things that are present in this particular block diagram? This is the input signal V in, this is the output signal V naught, this is an amplifier with open loop gain A given by V naught by Vi, this is the feedback network having a feedback fraction beta, and the input to the feedback network is V naught, and the output of the feedback network is Vf. So here again this Vf is given by beta times V naught, the same as that of negative feedback amplifier. Like construction wise everything same, only difference you can see here is the feedback is in phase with the input signal, so there exists a positive feedback. As a result, the effective input applied to the amplifier will be more and the gain will be more. Now, using this block diagram, we have to derive the expression for the closed loop voltage gain AF, and then from that expression of the closed loop voltage gain AF, we have to study the behavior of this particular circuit or behavior of this particular block diagram, and we have to come to the conclusion that when this amplifier with positive feedback can be used as a what? Oscillator, and that itself is called as Markuson criteria of oscillation. So to understand or to state what is Markuson criteria of oscillation, first we will try to derive the gain of this particular positive feedback amplifier, that is AF. So in order to explain the Markuson criteria, as I already told, consider an amplifier with open loop gain A equal to V0 by Vi. Let beta be the fraction of the output fed back to the input, so that the feedback signal Vf equal to beta into V0. And also from the block diagram, you can see that Vin is the source input, Vi is the input to the amplifier, V0 is the output voltage of the amplifier, and Vf is the feedback voltage. Hence, the closed loop gain for this particular amplifier, that is AF, is given by V0 by Vi. Now, the derivation for this is almost same as that of the negative feedback. In fact, the same derivation in the previous lecture we have done twice. One for the general negative feedback block diagram and one for the voltage series feedback amplifier. The derivation is same. Here also everything is same. Just a difference is of one sign. The negative sign is converted to positive sign here. That is the only change or the difference you have to do in the derivation, and you can arrive at the what? Closed loop gain or the gain with feedback. Like already we have derived the gain of the negative feedback amplifier AF as A by 1 plus A beta. Now, since we are changing one sign here, there will be a slight change, almost similar expression you are going to get. And what is that? You can see here in the next slide. Again, from the block diagram, the effective input applied to the amplifier is the external input plus the feedback signal. That is Vi equal to Vin plus Vf. Earlier case we have used minus sign. Why? There was a negative feedback. Now we are using plus sign here because of positive feedback. So Vi is equal to Vin plus Vf. We know that Vf is beta into V0. So if you substitute that, it becomes Vi equal to Vin plus beta into V0, and from this we can write Vin as Vi minus beta into V0. See, with negative feedback we got there it as Vi plus beta V0. Now with positive feedback we are getting it as Vi plus beta into V0. Now if you substitute this in the equation 1, what is equation 1? AF equal to V0 by Vin. So we can substitute this Vin value there. It becomes AF equal to V0 by Vi minus beta into V0. Again same, from the denominator we'll take Vi common. So V0 divided by Vi into bracket 1 minus beta V0 by Vi, or it can be written as V0 by Vi divided by 1 minus beta into V0 by Vi. And you know that what is V0 by Vi? It is A. So if you substitute that there, what you get is AF equal to A divided by 1 minus A beta. Now what you can see from this, it is almost same as that of negative feedback amplifier. Once again I am repeating, in negative feedback amplifier we have got it as A by 1 plus A beta, and here we are getting it as AF equal to A by 1 minus A beta, which is obvious because here we have used positive feedback. So with negative feedback we got plus sign in the denominator, whereas with positive feedback we are getting minus sign in the denominator. So most of the time you will get confused. Like here, important thing that you have to remember is, in negative feedback in the denominator you are going to get positive sign, whereas in positive feedback in the denominator you are going to get negative sign, because most of the time we have seen positive feedback, so student will try to write positive, that is 1 plus A beta, and for negative feedback they tend to write 1 minus A beta. It is opposite, right? So the gain of a positive feedback amplifier is given by AF equal to A by 1 minus A beta, where A is the open loop gain and A beta is called as the loop gain, right? Product of A and beta is called as the loop gain. So what we can see from this equation is the gain, overall gain AF depends on loop gain A beta, because AF is equal to A by 1 minus A beta. So as you go on changing the value of A beta, what happens? For example, suppose if A beta goes on increasing, when the value of A beta is increased, the effective value of the denominator goes on decreasing. As a result, AF goes on increasing. But when A beta becomes equal to 1, when the value of A beta becomes equal to 1, what will be the value of AF? It is A divided by 1 minus 1, that is A by 0, and the gain AF becomes infinity. So what it means? As the value of A beta increases, the gain AF goes on increasing, and when the value of A beta becomes unity, the gain AF becomes infinitely large, and the amplifier start functioning as an oscillator. So this is the essential condition of an amplifier to function as an oscillator. That is, when the loop gain A beta becomes unity, the gain becomes very large, theoretically infinite, and the amplifier start functioning as an oscillator. And this itself in fact is the condition for Markuson criteria. Hence the Markuson criteria can be stated as, for sustained oscillations, the loop gain A beta must be unity. But this is not the only sufficient condition. There has to be one more, because we can make this loop gain A beta equal to 1 in negative feedback amplifier also. Hence, to get the sustained oscillation, there has to be a positive feedback and the loop gain A beta equal to 1. Hence, for sustained oscillation, the loop gain A beta must be unity, and the total phase shift around the loop must be 0 degree or 360 degree or multiples of 360 degree. This is very important part. What do you mean by the total phase shift around the loop should be 0 degrees or 360 degrees or multiples of 360 degrees? This indicates that compulsory there has to be a positive feedback, because when you say phase difference is 0 degree, both input and feedback signal are in phase. Or when you say phase difference is 360 degree, again both the input and feedback signal are in phase. That means the bottom line here is always the input signal and feedback signal should be in phase, and that is possible only when there is a positive feedback, and the positive feedback is ensured when the phase difference along the loop becomes 0 degree or 360 degree. So once again I am repeating, Markuson criteria can be stated as, for sustained oscillations, the loop gain A beta must be unity and the total phase shift around the loop must be 0 degree or 360 degree. Then only the amplifier can start functioning as an oscillator. So the essential conditions for amplifier to function as an oscillator is the total loop gain A beta must be unity, and the total phase shift around the loop should be 0 degree or 360 degree or multiples of 360 degree. That is the important principle of oscillation called Markuson criteria of oscillations. Again I am repeating, A beta equal to 1 and total phase shift equal to 0 degree or 360 degree is called as Markuson criteria in simple words. So many a time they will ask the question, explain the Markuson criteria of oscillations. So what is the expected answer here? So you should consider a positive feedback amplifier block diagram, derive the expression for its gain, that is AF equal to A by 1 minus A beta. Then you make the comment from the above equation, it is seen that the gain depends on A beta, and as A beta increases, gain increases, and when A beta becomes unity, the denominator becomes 0 and the gain AF becomes infinite, and the amplifier start functioning as an oscillator. And then you should write the statement of the Markuson criteria. That is how you have to do when it is asked to explain what is Markuson criteria. Now, what is the effect of this loop gain A beta on the oscillations? If you want to have sustained oscillations, like sustained undamped oscillations, if you want to generate from the oscillator, compulsory A beta should be equal to 1. But if the value of A beta is not exactly equal to 1, if it is greater than 1 or if it is less than 1, what happens? That is explained in the next 2 slides. That is effect of loop gain A beta. You can see here, when A beta is equal to 1, we get undamped oscillations or sustained oscillation of fixed amplitude and fixed frequency. And as already told, amplitude and frequency of the generated oscillations depends upon the circuit elements that are used in the circuit. So when A beta is 1, we get what is called as sustained oscillation or undamped oscillation. But what if A beta is greater than 1? You can see here, when A beta is greater than 1, you get what is called as overdamped oscillations. Now what do you mean by overdamped oscillations? The oscillations whose amplitude goes on increasing with respect to time are called as overdamped oscillation. That is, when A beta is greater than 1, magnitude of A beta is greater than 1, we get overdamped oscillation. But if you make A beta less than 1, then we get the oscillation whose amplitude goes on decreasing, and these are called as underdamped oscillation. So when A beta is greater than 1, you are getting overdamped oscillations. When A beta is less than 1, you are getting underdamped oscillations. And when A beta is equal to 1, you are getting what is called as sustained oscillation or undamped oscillations. So normally in oscillator, initially the value of A beta is made slightly greater than 1 to generate the oscillations easily, and then the value of A beta is adjusted to unity so that we get the sustained oscillation after satisfying the Markuson criteria. So that is about the effect of what? Loop gain A beta on the oscillation. So we are interested in getting these kind of oscillations from the oscillator, and that is possible by satisfying the Markuson criteria. So in this class we have discussed basics about the oscillator. Now in the next part of this module, we have to discuss only 2 important RC oscillators here. We have classified the oscillators into various types, and as I said, based on the feedback network or feedback circuit used, we can classify the oscillators into 2 types, LC oscillators and RC oscillators. So here in your syllabus, we are not going to discuss about the LC oscillators because our aim is to study low frequency oscillations, and low frequency oscillations can be generated using RC oscillators only, because for low frequency LC oscillators are not preferred because the values of inductance and capacitance become bulky, and stability is also an issue. Hence, to generate low frequency highly stable signal, always we go for RC oscillator, and such 2 RC oscillators we'll be discussing in the next lecture, and those 2 RC oscillators are called as RC phase shift oscillator and Wien-Bridge oscillator. Right? What exactly the RC phase shift oscillator is? What is the circuit diagram of RC phase shift oscillator? How it satisfies the Markuson criteria and how it generates the oscillation, and what is the formula for the frequency of oscillations? That's what we are going to study in the next class along with the Wien-Bridge oscillator. Right? So with this we'll stop here. In the next class we'll be discussing about those 2 RC oscillators, and if possible we'll start the last part of the module, that is 555 timer. So what is 555 timer? What is its block diagram? Right? What is what are the different pins that this IC is having, and how this 555 timer can be used as an oscillator. So all these things we'll be discussing in the next maybe 1 or 2 classes, and that may be the end of this particular module 4. Right? Okay, thank you.